Hello everyone. This is Dilip Kumar, Assistant Professor, Department of ECE from Annamacharya Institute of Technology and Sciences, Tirupati. So in this video, we are going to see about RF system design tools, laboratory experimental sessions. In this video, we are going to learn the design and simulate impedance matching circuits. Especially impedance matching plays very important for the RF circuits from source to the destination side, because when impedance is perfectly matched, that results in maximum power will be delivered to the load with minimal loss. So matching circuits plays very important role in RF system design. So let's coming to this curriculum of the JNTU fourth year syllabus for EC students. The first experiment is design and simulate impedance matching circuits using L, pi, and T matching circuits. So in order to execute, design these three types of matching circuits, we are going to use QUCS Studio. So it is a quite universal simulator, circuit simulator. So especially impedance matching is one most important concepts in RF and microwave engineering. It ensures maximum power transfer between the source and the load while minimizing the signal reflections and improving overall system efficiency. These matching circuits or the networks are widely used in RF amplifiers, antennas, wireless communications, and even many more. During this experiment, we will going to understand the working principle, that is for the three types of circuits L, pi, T, how we are going to match with the load with respect to the circuit type of components, that is RF components, R, L, C components with respect to the input port, and followed by execution, that is simulation. Later, we are going to see about the S parameters, because S parameters shows us the impedance performance, matching performance at the source side and even at the load side. The major two parameters we are going to consider, as it is a two-port network, that is input and output side, we can have four combinations of S parameters can be achieved. One is S11, S12, S21, and S22. Basically, we are going to focus for the return loss or the insertion loss that is related to S11 and S21. Followed by, we are going to see the different matching techniques for this. By the end of this video, we can able to design, analyze the impedance matching networks, and understand where each matching technique is preferred for the practical RF applications. So let us get into this matching circuits first. Here you can see in the screen three different types of matching circuits. That impedance at the source side is denoted as ZS, source, and at the load side impedance is given as ZL. Between source and the load we have a network that can be generally called as a, that is also having certain impedance with the components, RF components, inductor, capacitor, and resistor as well. So for these three structures, we are going to design in QUCS software in order to obtain a good matching network with possible uh, minimal loss at the load side. So this is some basic structure here. It is shown the first column, you can see L matching circuit and corresponding Q factor and advantages and applications. And the bottommost figure that we can see here representing the graph is a Smith chart. Along with the Smith chart, we can able to plot Cartesian plot and even the three-dimensional Cartesian plot in QCS software. That is also we are going to see. Followed by the second column represents the pi matching circuit, and the third column is T matching circuits. So let us move to the software to design these three corresponding networks. In the previous video of this QUCS course, it is experimental RF system design tools. We have seen the introduction part of the QUCS software. In continuation to that, we are going to design L, pi, T circuits in QUCS software. So when we open the application of QUCS, we can initially see this window representing the empty schematic on screen. So first of all, we have to create a new project under every experiment, because every experiment belongs to different type of networks will be present. So on the left side of the screen, we can see there is a panel available with the option new. If we click that option, we can get the assign the name for that project. So I have assigned with experiment 1, creating a new project. If we create, then it moves to see the other different sections that comes under project experiment 1 has been created certain options, data sets, data displays, and even other files that has been created. So in order to create LT pi circuits, we have to stay in this schematic itself. In order to place the components on the left side in vertical column, vertical panel, you can see projects, content, and components. So place the components, click the components, and place the corresponding components for the L, T, and pi circuits. So let us design the L circuit. So to design L matching circuit, we need RF components, resistor, inductor, and capacitor. So those components are placed here. One, I placed inductor, then capacitor. So if we place the capacitor and inductor, the mouse pointer holding the component, in order to eliminate that holding component, press escape, then it will be removed from the cursor. Then place a resistor, and for the RF circuit, we need a source values, source input, and load side. 2 ports is to be connected. So for that, we are going to select sources section under scroll down, select sources, and select the source as a power source. So because why we are choosing the power source is that power source selected have an impedance value 50 ohms as a default value. Now for this inductor and capacitor, change the values of inductor to 56, keep the units as it is, nanohenry, and make sure for every RF component or the port or that any device component has placed under the schematic, before the units, there should be some space for every component. After editing the component, click apply and then OK. Then it will be edited in the schematic. For capacitor, edit to 22 picofarad, click apply, OK. So in order to turn over the components, you can have an option, turn component to vertical position. Similarly, let us change the resistor component to vertical position for the perfect matching of the circuit to shape L. Then take the wire and connect all the components from port 1 to inductor and from inductor to capacitor C1 and from R1 resistor to this junction node of LC and from port P2 to this junction. Then at the bottom side of the network, let us take to connect with the help of ground. On the top of the panel, you have different sections of components also available. So I have taken the ground and place the ground at the corresponding components. Then I'm changing the port to the value of 105 for the good matching. Then click apply, okay. And the resistor value is 100 ohms. Click apply, okay. Then after placing the components, save the schematic by selecting the option save. Save the schematic with the name of the corresponding circuit. So as it is a L matching circuit, I have placed the L matching and click save. Then it is saved. Then next step is we have to simulate this one. For that, we need to evaluate after executing of the circuit, the simulating of the circuit, we need to proceed for the analysis of the S parameter. For that, once again, select the scroll down option, go to simulations, select S parameter and place it here. Then we have the RF circuit is to be analyzed for the set of frequencies with starting and ending frequencies. In order to do that, we have to double click on the S parameter simulation, then proceed to change the value of S parameter simulation starting from 1 megahertz to 300 megahertz for this L matching circuit. And you can see the number of points given here that can be changed accordingly. So maximum number of points representing that perfect smooth curve for all the frequencies between start and stop represents a good graphical representation in the output. So we can have some maximum number 200, 250, 300, some value is been given as a number of points to be plotted on the graph. Then click apply and then OK. So as S11, S21, all these S parameters is to be displayed in dB, that is power values, output power is displayed in dBs. So the QUCS software directly cannot convert to decibel values. In order to convert that, we have to place the equations that is on the top of the screen. You can see there is an option called insert screen. Click the insert screen, insert equation, then place it somewhere. As I have placed two equations, one is for S11, the other one is for S21. Double click on the equation. Here you can see y is the left hand side of the equation. That is for our understanding, we can place that as S11 in terms of dB. So this is the name, dbs11 is the name. Then here on the other side, replace the one as small d, capital B, open parenthesis, capital S, square brackets, 1 comma 1, close the square brackets and then open, close parenthesis. Then apply and then OK. Similarly, do the same step for the equation 2 representing for S21. Replace the value. Make sure the S should be capital. S2 comma 1, close the brackets. then click apply and then OK. Now the corresponding all the required components, ports, simulators are placed here. After this, then once again click the save option. Once it is saved, then the schematic is successfully saved here. Now, completing all these tasks, let us proceed for the simulating this circuit, that is L matching circuit. So to simulate, we have to click the button on the top of the screen. You can see there is a symbol for the simulating the circuit. So click this symbol, then directly it moves to the other part of the window for the plotting the graphs. Then by default, left side of the screen, we can see diagrams section has been opened as a default because for the output. We can see different types of plots is available: Cartesian, polar, tabular, schematic, Smith chart, and even more admittance plot, 3D plots, all these things. So for the basic understanding, let us move for the Cartesian plot. Click this Cartesian and place it here. And once it is placed, then we can see a window has been opened with respect to Cartesian plot that is being showing different options of the data set for the DB S11, S21 and all other parameters S11, S21, and this below this four parameters does not have a conversion of dB. Only the first two set of parameters is being converted parameters of power in dB. So let us select those two and it's been plotted. So just click and double click on it. That will be moved to the other section of the graph. From data set to graph it moves. Then similarly for dB S21, double click and place it move other section. Then click apply and then OK. Now it is been plotted. Now let us a bit zoom it by extracting the image in diagonal so that we can analyze the plot properly. So here two waveforms is obtained for the single Cartesian graph, as we have been opted two S parameters is to be plotted. The first blue colored is S11 representation, that is S11 represents the first one is the output port, second one is the input port. So within the source side, is there any reflection take place? Generally, as per the basic standards, the S11, that is return loss, should be the very lowest value, it is less than minus 20 dB is a major generic value has been considered for most of the practical purposes. So based on the circuit what we have designed for the L matching circuit, we have obtained even less than minus 60. So it represents that we have obtained the circuit as a good matching circuit. In order to identify the value of this insertion loss, for return loss, we have to be taken up a marker to note down the value. For that, we have an option called M, set a marker on graph. Select this one and place it at the peak point of the blue colored graph plot. Then it shows the corresponding dB, power, S11 and frequency. Here, the graph of the x-axis is a frequency, y-axis is power in dB. Here 2.2 E power into 0.7. Here E represents the 10 and 7 is the power value of the 10. So here 2.2 into 10 power 7. So if we move one decimal of the 0 to the 2.2, it has been multiplied with the 2.2, then we can get 22. 22 into 10 power 6, which is nothing but 22 megahertz. For the 22 megahertz, we got a good resonant frequency with the return loss of S11 minus 66.4. So whichever the least peak value that is been obtained, that can be selected as a return loss. And the other one, we can see the red colored is showing that we have almost insertion loss with respect to the input and the output of S21. We have almost the reflection coefficient is being very near to zero. That is the most suitable for the matching circuit. Similarly, we can obtain the corresponding set of power values in terms of dB. For that, you need to select the tabular and place it on the screen. Then double click on corresponding dB values and place it here so that we can get this value, and it is being plotted. And if we want to see the three-dimensional plot, that is also possible to see. The same Cartesian plot has been seen in three-dimensional representation. The graph blue colored one and red colored one is S11 as well S21. Both has been seen. So like this, we have to analyze the S parameters in QUCS for the RF circuits. So let us go with the another circuit, that is RF circuit, pi and T circuits. Let us see. This circuit, you can see that is a T circuit with two ports. One is at the input and the other one is output. The structure of the network is a T type with the components of RF, R, L, and C components. So structure is a T shape, and this both ports has been matching is to be checked with the frequencies. A set of frequencies with the help of S parameter has been opted. Starting frequency 1 mega and end frequency, that is stop frequency, is 500 mega. The same points we can increase or decrease. Roughly we can keep the points always greater than 150 or 200 so that we can obtain a smooth plot on the graph. And two equations also has been inserted for the sake of plotting S11 and S21 parameters in terms of dB. So once it is done, save the circuit and then proceed for the executing this network. So then click on the simulate on the top, in the middle of the screen, you can see simulate. Click that button, then it can move to the plotting window. Then once again, place the Cartesian, double click on the corresponding S11 and S22 in dBs. Click apply and then OK. Now here we can see the plot is being obtained. The blue colored is obtained for the value. So let us take the marker and place it here at the bottom of the blue colored line for this one. It is a return loss. Now it shows the value of minus 31 dB for the frequency of 5.84 into 10 power 7. So which is in terms of megahertz is 58.4 megahertz. That is a resonant frequency we obtained. So this is for T matching circuits. So let us proceed for the pi circuit now. So for the pi circuit, the structure should be representing pi. So I have placed the ports and let us take the components. So here let us place the capacitor and another capacitor here and another capacitor here. Then click escape. Then proceed for the inductor to place to form a pi network. And we need one resistor, that is also place it here. And let us organize all these components properly to form the structure of pi. Okay. So let us do that one at the fast. So connect like this also we can do that. Connecting the circuit Using this, place the components near to that nodes so that easily it will get connected. And then let us turn this capacitor, make the structure of pi. So placing nearby nodes of the corresponding components, it forms the structure. So connect. This also we can do. It is also possible. Turn over the position of the resistor and place it, drag it. And once again, the other capacitor also place it here. And then, so we have the port here. So that is to be connected at the end part of the pi network. So for the resistor and capacitor, we don't have the grounds. Let us take the grounds here and then click escape. Let us take the values here. The capacitor, place it here with the value of 56 picofarads, and the same capacitor also is being taken here, 56 picofarads. Do it. And then inductor is, let us take for the perfect matching, 68 nanohenry, or roughly you can take approximate to 60 also. And the resistance value is being taken as 100 ohms. And then capacitor is considered once again for C3 is 56 picofarads. So after editing, that is changing the values of all the RF components and placing the equations, S parameter, everything is done. So here, after completing all these tasks, so we need to check for any connection errors or anything else. If suppose if any connectivity errors is being obtained, then if you click the simulate, it shows some kind of error sometimes. So that is also possible. So here we can see, suppose if you done any mistake, as I said earlier, suppose if there is any no spacing between the units, so then click apply and then okay. Now let us see, there should be some error. So it is not showing. Sometimes it shows errors. So make sure those errors should not occur. Okay. So if everything is fine, then click the save and then proceed for the network to be simulated properly for the S11 and S22 parameters. So click on simulate and we can see here that it is been obtained for the network. So I have designed in the pi circuit even the same schematic, that is why it shows L. Don't bother about that. So if been plotted, then we can see here the blue colored one is a return loss S11. So let us check what is our frequency. Is it very near, less than to minus 20 dB is almost obtained with minus 21 dB, which is less than minus 20 dB. So it is a good impedance network also obtained. And we have the for the same value also we have that S21, that is insertion loss also has been recorded here. So like this, using markers we can obtain the values, and even for tabular column also representing corresponding S11, S22 values also will be seen in the tabular column, representing for the different frequencies, whatever the start and stop frequency that is given in the S parameter simulation, that will be obtained for this pi network. So with this, we can understand that we can able to design the matching networks for the three different types, L, T, and pi shapes. You can analyze the impedance matchings for the different three types of networks, which is used for the practical RF applications. Thank you.